do this.
It's a little thing.
Only four of you today, huh?
So far, yeah.
Still early.
Sorry about the other day, James, but you blew it, and I blew it.
Oh, that's okay. I just had to. There was a pretty big thing I had to do. I didn't really have much of a.
Hold on.
Words are hard.
Well, let's see. Hold on a second. I'm going to pause. So I did, see, I thought that I'd maybe forgotten to give that to you because I would have handed it out in class sometimes. So I must have posted this online. Okay, so what we're looking at here with this, let me share the screen. Put you guys over here. I need to make it bigger. Oh, except I can't make this thing larger with only 3 students. This is stupid. I hate this about, I want to make these pictures bigger. Oh well. Let me get my Epic pen out. Sorry, I'm sneezing. That sneeze is very up in the nose sneeze, which means it's allergic to something.
It's a sneezy kind of day, I guess.
It is. Okay, so I'm going to undo this, get to my pen. So what I'm saying is here, I have got these forces around an area of low pressure. And the area of low pressure is going to be the pressure gradient force pointing in. Like this, right? That's where the pressure gradient, it points from high to low pressure. The velocity of the wind is like such, and then the Coriolis force is going to be perpendicular to the right. Now in this case, as you're going cyclonically, the centrifugal force, which they put as CE, and I've done centri, is outward. And what that means is I'm looking for the pressure gradient force has to be balanced by the Coriolis force plus the centrifugal force. Now this force is velocity dependent. This force is velocity dependent in terms of velocity squared. And this is just, what I like about the pressure gradient force, it is. That's all it is. It's the pressure gradient force. Whatever the pressure gradient is, that means there's a pressure gradient force. Okay, so I've got a balance between these two forces. So what happens if I make the pressure gradient force larger? If this force becomes larger or smaller, what will happen as the strength of the pressure gradient increases or decreases? The answer is these two forces here are going to change to balance this pressure gradient force. So just like we said in the geostrophic case, the gradient case is going to be the same. The pressure gradient force can get larger, and those other two forces are adjusting to balance it. That is what they're trying to do. And they adjust to balance it by changing the velocity. That's why we get subgeostrophic, right? The subgeostrophic case. However, when I look at the equations of motion and I solve, remember this is the C term, this is the B term, that's the A term, because this is the binomial, this is the linear, and that's it's not dependent on velocity term. When I do the equation and I go, it's minus B plus or minus square root of
E squared
minus 4AC all over 2A. And the idea of this is that this term, as long as it stays above 0, which it always will because the pressure gradient force is opposite the centrifugal force. So that means A and C are going to be of opposite signs, the vector points in different directions. And a minus is going to be positive. B squared is always positive. So in here will always be positive, which means I'm going to get the Coriolis term here plus or minus some other term. Now, the term can be big enough that I get weird numbers, and I'll show you that because, Jim, you had 2 answers, right? And one of them comes out to be this case. Now, in this case, what we're saying is that the pressure gradient force is still pointing this way. But the Coriolis force is also pointing in the same direction. In other words, the B term and the C term are the same sign because the velocity is going in an opposite direction. By the way, it's also very large velocity because as the velocity gets larger, the centrifugal force grows how?
Exponentially.
Exponentially. Right? So we have an exponential growth of the velocity, which means you can make the pressure gradient force as big as you want. Pretty soon, the centrifugal force is going to become dominant. It becomes so large because it's growing exponentially that you get a force large enough to balance those other two. The point is, this is a mathematical equation. The problem is the the gradient wind comes about by actual winds. So we call this the anomalous case, which is going to show that it's a negative velocity from what it was before and very large. The point is, based on the way weather works, we tend to get areas of low pressure that start to developing relatively slowly. And in a slow change, the pressure gradient force grows at certain amounts and then are balanced as it becomes circulations. The anomalous case is not going to happen naturally. We're not going to see areas of low pressure that do this, that go in the opposite direction. Because you can't slowly build this case. Now, if you started it, if I created a mechanism where I could do a marble going in another direction, whatever I wanted to do, if I did it artificially, I could solve that force equation and get this case. But it won't slowly get there. So that's what I mean by an anomalous case. So it says this over here, that letter A is this, letter B is this in an anomalous case. Now, there comes a time where sometimes the pressure gradient is really big and the centrifugal force is really, really big. Now, you would think, well, the Coriolis force is getting larger and larger and larger. But remember, when I look at the equations of these forces, we have the pressure gradient force plus the Coriolis force equals the centrifugal force. That's this anomalous case. Okay? In that scenario, the centrifugal force, and we really ought to think about this in terms of linear versus exponential growth. So there's a graph. This is what linear growth is, right? Oops. Linear growth is like this. Exponential growth is like this. It always starts out slower, but soon becomes dominant. It's growing by the square. So even if I start getting a large Coriolis force, the centrifugal force will dominate it by a lot. So I double the Coriolis force. Well, now this is 4 times bigger. And remember, it still has to be balanced with the pressure gradient force. So if I scale this equation, this term is going to go away. These terms are going to easily become 10 times larger than this term, because the Coriolis force, no matter what, is dealt with 7.29 times 10 to the minus fifth. I've always got that term in there. So these become positive, and no matter how fast the velocity is, I'm always going to lose, 4 or 5 orders of magnitude because of this term in there. And even though this velocity. So when I get an idea like this, where the pressure gradient force is balanced by the centrifugal force, and I have no Coriolis force whatsoever, or I've scaled it out, this is called cyclostrophic. So cyclostrophic balance is the balance between the pressure gradient and the centrifugal force. Now the question is, can you give me an example of something that is cyclostrophic? What do you think?
Would a hurricane count as cyclostrophic?
No, because a hurricane's always cyclonic.
Oh, that's cyclone.
Anybody?
Tornado?
How about a tornado? Isn't a tornado?
Oh, yeah, those are not cyclonic, are they?
Well, a tornado doesn't have to be cyclonic, right?
Nope.
So what I'm saying is in the large scale, this thing is occurring so slowly that it's always going to go to cyclonic. So a synoptic scale cyclone will always be cyclonic. But when we get down to the mesoscale or microscale, I can get cyclones that are anticyclonic in terms of its direction. But in a tornado's case, is it super geostrophic? And the answer is no, it's cyclostrophic. The Coriolis force gets scaled out of that tornado's existence.
Okay, and that's where you said that that other extreme answer was coming out of the quadratic equation was the cyclostrophic.
That is correct. And that can happen. But again, to get there, it's not going to be from something slow. So what's going on with the tornado is that you're not generating changes in pressure that are slowly going to start to change the wind direction. It's the whole idea of water going down the sink cyclonically. The change is occurring so slowly, you're not able to actually get to that on the large scale when it's taking a long time. But a tornado happens very quickly. And what we're finding out is that we have anticyclonic vorticity that is created from that vortex arch when we start bending vortex tubes and then stretching them as we accelerate air. So in other words, we don't generate this gradient balance first. We've got strong amounts of shear where the Coriolis force is playing a really insignificant case. And that's really what you need to think about is on the tornado scale, the Coriolis force doesn't have a lot of influence. Now it does if you last a long enough time, but here, let me show you something. I've got, let me do it this way. I'm going to go back to academics, class notes, because I have this in my intro notes. And I look over here. So if you look at this example, let's look at a tornado. So what we're assuming is a velocity of 50 meters per second. The radius is 200 meters. Latitude 40, sine of 40 is 0.643, right? And then the centrifugal force is V squared over R. Therefore, the centrifugal force, if you look, is 12.5 meters per second squared. The Coriolis force is what? 4 orders of magnitude smaller than this? So we have this huge force. Is there anything that can balance that force? And the answer is yes, the pressure gradient force can. And that's when we start to say, well, how big would the pressure gradient force be in a tornado to come up with the 12.5 meters per second squared? Can you do that? Let's do this. So I have 1 over rho dpdn. Now, for the sake of it, let's just go that rho is 1.25 kilograms per meter cubed. Now, the reality is the air is under such low pressure, you're going to probably get a much lower density. So for the sake of trying to be a little bit more realistic, let's drop this to, well, let's just make it easy. Let's make it 0 or 1, so I don't have to deal with this term. So that means I'm looking at what is the pressure gradient, and it's this whole thing will be meters per second squared, and it has to be equal to 12.5 meters per second squared. So what kind of pressure changes over a distance? How wide is the tornado? Well, let's take a tornado, and we said we're going to assume that the tornado has a radius of 200 meters. So the pressure change, what does that have to equal? Well, what's 200 times 12.5?
1,500.
Right? It's going to be, no, 2,500?
Oh, 2,500.
Mm-hmm.
2,500 what?
Pascals.
PAs? Or
Millibars?
no.
It's got to be pascals, right?
Pascals.
Yeah.
So how do I get that to millibars?
Divided by
100, right? Hectopascals.
less.
So what that means is my pressure change should be about 25 millibars. So if I have a tornado that's 200 meters in the radius, and the velocity is 100 knots, 50 meters per second, so 100. It's not a super strong tornado. The pressure drop is going to be about 25 millibars across that 200, right?
Mm-hmm.
So 25 millibars over 200 meters, man, that would be windy. Well, yes, but that wind is cyclostrophic. I don't need to know this wind, the Coriolis force, because it's insignificant. It just scales up. And then in here, I did it with an area of low pressure, and the Coriolis force is actually larger than the centrifugal force, unless it turns really quickly. So if I talk about tornado pressures in the eye, I'm trying to think what I need to look at.
There was something there.
I'm looking for something. Here we go. Okay, so here's the pressure that they measured in here, where they looked at the pressures going from 950, and in the center of the tornado, it dropped down to 860 millibars. So you're looking at a 90 meter or a 90 millibar drop in pressure over around 200 meters. So that's 3 times stronger, which means instead of being 50 meters per second, it's about 150 meters per second. And now we're looking at a very, very strong tornado. Of course, we haven't figured out friction, because viscosity would actually play a role in here. And there may be, the problem with the tornado is it's not in pure cyclostrophic balance. Do you expect tornado winds to be going around completely? Like in a circle? What do things tend to do? They tend to fly out tangentially, so there's a centrifuging effect. So I'm not sure if cyclostrophic balance is actually met. But nonetheless, when you start looking at these equations, where's my diagram? When you start looking at these equations, that's what you come up with. Now, an area of high pressure is going to be the same thing here as well. However, because we have a pressure gradient force that is pointing outward, if this force gets large, if it starts to get larger, what force is allowed to try to balance this?
Sentry.
No.
Coriolis.
Coriolis, sorry.
Right? The Coriolis force does. So if it gets larger, but how do I make the Coriolis force larger? The velocity has to increase. But when the velocity increases, what happens to the centrifugal force?
It's going to go up
by a lot more. So at some point, I can't solve this equation. What is the limiting case for that? Well, the limiting case, if I think about this, if I think that the velocity is minus b plus or minus the square root of b squared over 4ac all over 2a, then I know that b squared must be larger than the magnitude of 4ac. Does that make sense to you? Because A and C, the centrifugal and the pressure gradient force, are acting on the same side, so their signs are going to be the same. And if 4ac is too large, the Coriolis force can't solve it. So in your book, there is a problem I'd like to see you turn in. Now, I need you guys to be turning in stuff, because right now I'm trying to give you a grade based on this final workbook, but I also give you these other assignments, and I'm not getting answers from you. So your grades aren't going to be very good because I'm not getting that stuff from you. So there is a question in here. Where is it? Let me see. We did 716, which not all of you responded to. What I'd like you to do is, I want you to do some problems in the book for next week. 718 and 719. I also would like you to do 721, because that's a total derivative problem, which we've already kind of gone through. Then 724 is what I want you to show, which is, this is what we're talking about here on the screen.
So 7, 18, 19, 21, and 24?
Yes. And that's what I want you to do for next week. Well, in any case, because I still have a limiting thing, plus or minus this is going to end up with an anomalous case, just like this low pressure area. The only difference is this anomalous case has two velocities going in the same direction. Okay, so when I go from B to D, the anomalous case, what's different? Well, the Coriolis force is larger. The centrifugal force is larger, but what's smaller?
Pressure gradient.
So I can get the anomalous case with the smaller pressure gradient force. The point is, this thing that I had you do, this thing up here, that idea says that the supergeostrophic case is limited by the strength of the pressure gradient. No, that's a bad way to say it. The supergeostrophic case has a limit to the pressure gradient. In other words, I can only have the air curve anticyclonically so much before I can't solve the equations. So when I look, let's go over here, when I look at something like this, models, and I look at the GFS, and let's go to North America, 500 millibars. Notice that in all of the speeds of the winds, what color can I get? Blue. I've got strong winds, strong winds in the trough, strong winds in a 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 trough. But look at the ridges. Weaker winds. Weak winds. Weak winds in that ridge. So all of the places where I start to see a ridge, I see the air slow down because it can't make the curve. Which means if the air is coming, let me maybe find a better place to show you this. Let's say over here. As the air is coming here, it's not going to make the curve if it's going too fast. So when I say it doesn't make the curve, what does that actually look like? Not making the curve says what? It says that the pressure gradient force is going to be too strong. So not making the curve means the air crosses the isobars toward lower pressure. If air moves toward lower pressure, and this is at the upper levels, do you agree that's going to be convergence?
No.
Air is crossing the isobars. There's ageostrophic. Remember, like for you guys at your level, the number one fact about the geostrophic wind that you should think about is it's non-divergent. And I'm saying that the air is crossing the isobars toward lower pressure. It's going to be convergent. It's aloft, which means the air sinks. So what I'm saying is that the air is non-geostrophic. It crosses the isobars, and that isobaric cross modifies things. And that's what we're going to kind of talk about today. So let me open up my notebook, or whatever is left of my notebook. My notebook is falling apart. My career is almost over. And I'm going to do this. Okay, do you have any questions on this casing of the the normal and the anomalous cases here. So I think this is a good thing to remember. Obviously, we don't see it taught very much anymore. And I think that's a shame because I think this has got some really good value to it. Did I start recording? Yeah, I did. I started recording. So let me do this before I do anything else. Jim, where are you? Here's Jim's homework. Jim, that's why you said no, right?
Mm-hmm.
Yeah, okay. What I'm saying is it's divergent from a surface high.
Got it.
Crossing the isobars toward low pressure, it's convergent.
Okay.
You see what I'm saying?
Got
It's
it.
diverging over here, it's converging over there.
Right.
So all these things are really good. Notice too in the wave, he's got the super geostrophic. In between the waves, it's geostrophic because this part of the wave is pretty much linear, and then subgeostrophic. So that's good. Put this equation in there. All the equation comes out, and you get the geostrophic wind of 30.158 meters per second. Nick, that's the same thing you got, right?
Yep.
Okay, so that's 60 knots. Then he's using that formula for looking at the RT, which I've given you, and then he plugs and chugs, and he gets two answers: negative 19.5 plus or minus 39.4. So the first one is 19.95, which is the normal one. And it says must be non-negative, but this one would be the anomalous case that we just talked about. And notice that it would be much faster.
Well, okay, question. If it was imaginary, then you could totally discount it, correct?
Yes, yes.
Okay.
So an anomalous case means it's still solving the equation.
Right.
Mm-hmm.
So this one does. Now, in the super geostrophic, when you do this, you get 30 plus 19.5, 50.108, but they would also be the minus 19, right? 19.5. Wait, no. You can't do that. It's not symmetric. It's a different answer. So what you would be saying is that what you're basically looking at in this case is that you have 380.25, which is b squared, right? Plus or minus the square root of b. I'm sorry.
No.
Yeah.
19. The brackets are the square root.
B squared minus 4ac. So you need to plug in your 4ac and the b squared. Oh, I see what you're saying. I'm sorry. This is b squared plus or minus this thing.
No. Minus 19.5 plus or minus, and the brackets is what is the square root.
Minus b plus or minus,
right.
And this is
Square root.
There we go.
Mm-hmm. I'm assuming the 4 was thrown in there somewhere.
yeah, I'm assuming you got this right.
Yeah.
This looks right.
Yeah, I got that too. So, yeah.
But if we did the other case, then you'd say, well, what about if this is a minus sign? Because you've got it as a plus sign. What if this is a minus sign in here? And you're going to get different answers of this. Now, So don't just add the 19.95. I don't think you can just do that. So take this one, take 380.25 minus this value here.
Okay.
Can you guys do that for me real quick on a calculator?
Yeah. You get something that's imaginary, but
So this number, what's 4? Is this 4.1? No. 4 times 10 to
4
the
times 10
fifth.
to the fifth.
Yeah, just so you know, Jim, I think every time you do exponential, this should always be an x to keep it.
Okay.
So 4 times 10 to the fifth times 2.94. This is going to be 10 squared, 10 to the third. This is probably going to be bigger, isn't it?
$1176.8. Yeah.
So 380.25 minus that and the square root.
That's imaginary.
Imaginary.
Yep.
So in other words, that pressure gradient force is too strong for the curvature I gave you. So you can't solve the ageostrophic case. So let's do this. Let's take that.
Oh, this is a trick question. Okay.
yep.
Let's do something here. Let's make RT bigger. I think if you doubled it, if you doubled the trajectory, you'd solve it. You don't need to worry about doing that.
Okay.
That's fine that you're setting up the problem as well. But notice that that's not the way this works. You don't just take the opposite way. It's not like the subgeostrophic is so many meters per second slower than geostrophic. The supergeostrophic is not that same amount more than geostrophic.
Okay.
Right? Because the equations are nonlinear.
Okay.
So when I was doing this, I kind of assumed that, well, when you get ended up getting those imaginary numbers, and at least taking the magnitude of that imaginary number, because I converted it from, like, you know how you can put the imaginary numbers in like rectangular form and polar?
Yeah,
I was like, if you put it in polar, would that be like the actual value that would...
Mathematics deals with imaginary numbers. The atmosphere.
Yeah.
The atmosphere ain't imaginary.
You can use fluid dynamics using imaginary numbers to get a principle out of it, but the flow itself cannot do that, is what we're saying.
Okay.
So in this scenario, with that flow that you have, if it that's weird. Back.
Well, there has to be some value of the wind that's still gonna come out of that case, right?
No. What I'm saying is that when you have this flow trying to go under this RT, that radius and trajectory, right? It's too tight to balance the pressure gradient force. And there's no real combination of forces that solve the equation, which means the actual flow doesn't make the turn. It goes this way. So imagine the flow is going around and it can't make the turn. Now we establish a new RT that's much larger that you can solve.
Oh, okay. Yeah, now that makes sense.
But because the air is flowing toward low pressure, you're slackening the pressure gradient.
Yeah.
You're traveling. You know, the Moses. You guys remember what I do for you the Moses' fish tank?
If you did, I didn't see it.
You know what I mean by that? Moses' fish tank. I've got a tank of water, and because Moses can part the Red Sea, I said, what if I saw a tank of water that looked like this? Okay? Do you understand that this water is going to try to flow this way until the water level is straight across? Mm-hmm. That's what it's doing. It's going from high pressure to low pressure. If you get water flowing this way, the pressure gradient force gets bigger. If you have water flowing the other way, the pressure gradient force gets smaller. So the only way to have it flow the other way is Moses, parting the Red Sea, moving the water against the way it would want to normally flow. So the air in this scenario is moving away from the high, toward lower pressure. Since it's moving toward lower pressure, the pressure gradient force is getting less. And remember, I said the problem with solving that equation is that the pressure gradient force is too strong. So by having the air flow at a lower radius of trajectory, it's now going to slacken the pressure gradient force. Eventually, you can balance that force out, and that's why we don't see these super strong anticyclones.
Okay.
Right? We don't see anti-hurricanes. We can see hurricanes because all we have to do is continue to make the pressure gradient force stronger and stronger and stronger, and the forces will balance. But if I take an area of high pressure and try to make the pressure gradient force stronger and stronger, higher and higher pressure, it can't do it. I can't solve those equations. Does that make sense to you guys?
Yep.
So if I get it, it's sort of like how if you can't solve it for a certain equation, it's just saying that that's not actually where the pressure gradient force is going, or the
Yes, right. So I gave you a scenario that has this pressure gradient, this radius of trajectory at some latitude, right? I'm saying how fast I'm giving you all the information, and I'm saying, tell me how fast the winds are. Given that information, you cannot figure out the winds because the pressure gradient's too strong for that radius of trajectory. It doesn't, you can't actually get that. It doesn't solve the quadratic with a real number.
all right.
That's what I mean. So in other words, what I gave you is false. It couldn't be that way. But on the synoptic scale, changes take place slowly. So the atmosphere never tries to do that. It just does not allow for strong pressure gradients in the other sense. Think about a hurricane. What makes the pressure gradient so strong? Heating of the column. Heating of the column through a huge amount of latent heat release is going to create divergence aloft. In fact, this is a really good thing. I have pondered this question for a long time. Okay, so what I want to do, and I'm sorry, I'm going to move away and kind of go crazy for a while. I'm looking at a hurricane. Okay, so a hurricane is an area of low pressure. And we say that this area of low pressure should have a pressure gradient force. It should have the Coriolis force. And there should be an outward directed centrifugal force. And these three forces are balanced. And therefore, the velocity of the wind is this. Right? That's the velocity of the wind. It's going around in a circle. But the hurricane near the water, even though it's not much, has what is present near the water? Friction. Right? So there's friction. So what does friction do to this whole thing? Friction acts opposite the velocity. So here we add the force of friction. Right? Friction is going to make this force smaller, that force smaller, because they are both what? Velocity dependent. Right? They are velocity dependent. So when friction plays a role, it's going to slow the winds down. It's going to cause the centrifugal force, V squared over R, and the Coriolis force, FV, to be smaller. Well, what does that mean to this original gradient balance? The original gradient balance was PGF balanced by these other two forces. It no longer can be balanced. So what does the air start to do?
Start speeding up.
It starts to cross the isobars toward lower pressure. Right? It's going to converge toward the middle. Because if I look at the balance of forces keeping it going in a circle, the balance is offset because these two forces are made smaller. The pressure gradient force therefore dominates and the air crosses the isobar. In fact, there's a problem in the book, I'm not assigning it, but it says, what's the angle that's necessary for this? And it's about 20 degrees. Well, this is good because that makes air flow toward low pressure, bringing in moisture. I get moisture convergence, which creates the continual warming of the column. Okay, does that make sense?
Mm-hmm.
Okay, now let's change this to above. I'm in the circle. Now I've got an area of high pressure. Now I'm going to draw this in here going high pressure has the pressure gradient force. We know that the Coriolis force should be pointing opposite direction, and the centrifugal force in this case is pointing outward in the same direction. So just keep in mind pressure gradient force blue, Coriolis force red, centrifugal force green. The velocity of the winds is that direction, anticyclonic, right? So these three forces set up a balance. If I add friction, which force is going to dominate?
Coriolis and centripetal.
No, what would those two forces do if I add friction?
Oh, they're going to get smaller, just like in the
They're going to get smaller, so the
Just like in
pressure
the other
gradient
case.
force wins, which means the air crosses the isobars toward lower pressure. It diverges from the center of the arc,
Okay.
right? But if that were the case, then how would the flow be?
Yeah.
Jim, you even drew a picture like this, right? It's going to diverge. But why does it diverge? Because of friction.
Friction.
But in a hurricane, there's no friction at the top of the atmosphere. So why does air diverge at the top of the hurricane? I know why it converges. Remember we talked about a hurricane spiraling in and then diverging aloft. Why does it diverge aloft anticyclonically if there's no friction?
Obviously, the forces are in balance, so.
So in other words, the curvature, if I had it, would be so tight that I can only do so much of a pressure gradient. But I release so much heat and create high pressure aloft so strong, that pressure gradient force cannot be balanced. If it can't be balanced, what does that make the air do? Go across the isobars to low pressure. That's why you get divergence aloft. It's because you can't balance that gradient wind. The hurricane's too small. Now it's going to be nowhere as noticeable, but you will see that divergence because it can't make the curve. You got to admit that's kind of cool, isn't it? Tell me that's cool.
It is pretty cool.
Do you understand that?
Mm-hmm. So it's the same principle if...
In other words, why is there, if that would be a great test question. And I'll bet you nobody at any university probably could give you a good answer. Why does the air converge cyclonically at the low levels of a hurricane? Well, friction crosses the isobars. Why does it do anticyclonically a lot? Can't make the curve. The geostrophic balance is not set up. The pressure gradient force cannot be balanced. That's what it is. All right, now, any questions on that? Let's talk about this converting to this. First of all, what is omega?
Angular momentum or angular velocity?
No, different version. Sorry, it's just a different thing. What's W? What's W?
Vertical velocity.
So what's the derivative?
dz dt.
So we're saying I'm using the vertical velocity in Cartesian coordinates as opposed to vertical velocity in isobaric coordinates, pressure differences. So do you agree that positive omega would be sinking air and positive W would be rising air? Say yes or no. Does that make sense to you?
Yes.
Okay. So if that's the case, I'm going to do this. This is just total derivative. It's time to remember your total derivatives. Now do you see how omega and W are going to be related? You know, what I've realized when I teach and why students struggle, and these are kind of things you're gonna, what I wish you could do for yourself, not for me, but for you, is there are certain things in math and science that you need to commit to fluency. The total derivative is one of those things. You need to do it. Well, here's the question. How do you get fluent in anything?
Practice, practice, practice.
Right? So you need to do it so many times that you don't even think about it. You're like, that's what this is. You know, that's why when I do stuff like this,
That's a question.
I want you not to even think. I want you to see something and immediately respond to that. I want your brain to be conditioned to that fact. So total derivatives are one of those things. Do you understand what I'm saying here? Tell me what this is. Tell me what this term is.
Change in pressure over time.
Okay, that is correct. What could you tell me that is? There's a name for that.
Oh.
And besides, it's not just the change in pressure over time. And the reason for that, Jim,
Because it's partial.
Isn't that a change in
Yes.
pressure over time? So what's the difference between those two?
One's Euclidean, one's Lagrangian,
Okay, Eulerian.
or Euler.
Right, but what? Yeah, you're right. That's true. But what? How would we just? That's called a what derivative?
Total.
Total.
This.
That's
Partial.
Partial.
It is a partial, but there's a name for it. That's the
Oh,
local.
local. Oh, I see what you're going.
You
Okay.
understand that? And a local is a material point.
Yes. Okay.
It's a station. So what do you
Right,
call
station.
what do you call the local change in pressure as time goes on? There's a name for that. Isn't that what a tendency is?
Oh, I never heard that.
Like, what's your 3-hour pressure change at a station? That's the local pressure change, right? And that's why you define terms, and then you need to convince yourself, oh, that's really easy. I know that. First thing we do in a station plot is we learn how to say this is plus or minus so many millibars in 3 hours. What's this?
The dot product of the velocity with respect to height and pressure.
No. What is this? What does this H mean?
Oh,
Like, what does this mean?
okay. The change in velocity.
Look, do you agree
The
that
horizontal velocity.
this is horizontal velocity, right? This is UVW is a three-dimensional wind vector, right? But I'm only looking at the horizontal component. So I'm really only saying, I'm going to look at just this horizontal wind for this term. That's why it's VH.
Oh, okay.
But
that makes sense.
what is this term? What do you call that?
Del P.
And when del operates, pressures of what kind of term?
Scalar.
When you have del operating on a scalar, what do we call that?
Gradient.
Okay, so we have a gradient, right? That's the pressure gradient. And what does it mean when I take the velocity times a gradient? What is that called?
Vorticity.
No,
Divergence.
no. Okay, once again, this is the other thing you need to commit. Del on a scalar is gradient. Del on a vector is what? I'm telling you, you need to memorize this. Your life will be so much easier if every time you see these terms, you go, that's what that is. What's this? That's the
for
curl. But if that vector is velocity, that's what we mean by vorticity.
vorticity.
If this vector is a velocity. But I didn't say, none of those are here. I already said this is your gradient. Velocity times anything is what? Why do you forget? Velocity times anything is advection. Does that make sense?
Yep.
Okay, so this stuff and your total derivatives, dude, do yourself a favor and put flashcards and look at it every day for a month. And do it every day for a month, and you will go, I will never forget this. Because that's, I'm giving you the secret of things I've learned through teaching. Don't forget this. You will be better than me if this is where you start. Because it took me a long time to get to the point where I go, oh, I wish I knew this. See, that's what I've done as a teacher. I'm like, oh, God, I wish I knew this all the time. And I started realizing, here's the important thing. Everything else, you know, and let's face it, do you agree that in math, sometimes you don't know what's important. You keep getting different, you get a topic here and a topic there and a topic there, and pretty soon you're like, the hell, I have 1,000 topics. I can't remember all of them. I wish somebody would come to you and say, this is what you need to know. The other stuff you can write down and look at it later. At least for me, that's how I would view calculus. I would teach you the foundations first and then apply them when I don't care about as much. But this I care about. And this stuff for meteorologists is vital. And Nick, you've taken all your math. When do you get this? When do you get this term, these terminologies in the del operator?
Last semester.
It's your very last semester. In fact, at COD, you take Calc 1, you take Calc 2, you take Calc 3, and then you get this 2-week course called, or 4-week course called Vector Calculus. 4 weeks at the end of Calc 3. And I say, are you kidding me? This is more important than anything else you do. Because these are all terms we use all the time. Would you agree? Okay, so this is the advection of the pressure gradient force. Now, for advection to be true, what do you need to have? For advection to exist, what must be true?
Some kind of motion.
You be more specific. Okay, I'm going to ask you a question, and don't say it out loud, but just half of my class is invisible, so show me that whether you know this. What's the difference between baroclinic and barotropic? Have you put that into your brain yet? Do you know the answer to that? If I said draw a picture of barotropic and draw a picture of baroclinic, what would you write down? Jacob, what would you write down? Or do you know the answer to this?
I'd have to go back in my notes and look. Not off the top of my head, no.
James, do you know?
I think barotropic is supposed to be horizontal shear, while baroclinic's vertical?
Nope.
Or am I thinking of a different term altogether? Probably.
Probably. Nick?
No.
Jim?
Baroclinic, the height and the thickness contours intersect.
And a barotropic? Yeah.
They don't. They're parallel.
Here's height lines. Z plus delta Z. And then over here, I can put in these lines. Z plus delta T, let's say. Do you agree that the air would be flowing this direction? Parallel to the contour lines. At least the geostrophic wind is. And this would be cold advection. Does that make sense? This is baroclinic. Now, Jim, you could say those are thickness lines, because thickness and temperature are basically the same thing because of what?
They're basically the same because of what?
Thickness and temperature are basically the same thing because of what?
Thickness relation?
What's that called? What's the technical name for that?
They're dependent?
No,
not
what's the technical name for the thickness relation? But you're not
Isotherm.
wrong.
Isotherms?
No.
No.
Thicker the warmer, the thinner the colder is what?
Oh, density.
Yeah, but what's the name of that equation?
Oh.
Hypsometric.
That's a hypsometric.
There's another thing you need to remember. Thicker the warmer, thinner the colder, which I know you know that, right? Hydrostatic, ideal gas law, hypsometric. We've done the hypsometric equation. That's in your notes. That should be a really huge section. Super great. But thickness is related to the average temperature of the layer, right? So if I've got isotherms, I'm similar to saying isothick. So baroclinic is when they intersect, because this is advection. So the wind, the geostrophic wind in this case, is going to be advecting temperature, because the isotherms and the isoheights or isobars intersect. If the isotherms were like this, then there'd be no advection. Okay, does that make sense to you? If they're parallel, they're barotropic. Technically, there's something we call equivalent barotropic. If they intersect, they're baroclinic. Are you good? Say yes or no.
So can you repeat the one for barotropic one more time?
They're parallel.
Okay, but that's parallel.
Well, no, I mean this other one. So if you get rid of those, that's parallel.
Yeah, that's what I meant. Sorry.
Okay.
Well, the notes I'm taking today end up being reminders of other notes I've taken. So that's probably
Well,
good.
I know that's why you take my teaching. I teach you things over and over and over again. But here's the thing.
Indeed.
Let's look at this situation. Here are two isobars. Pressure, pressure plus delta P, whatever. And then, what if I said, this is the actual wind? Now, I'm going to do it this way. This is the actual wind. Okay, so that is the velocity. That's the actually, because I'm looking down at a two-dimensional surface, that is the horizontal velocity. So that's VH. Do you agree? Say yes or no.
Yes.
Okay.
Yep.
Does that look geostrophic to you?
No.
Okay. So what is that really equal to? Well, VH is actually equal to this plus this. So what is this brown vector?
Geostrophic wind.
So that's the geostrophic wind. And what's this yellow vector?
What was that?
The ageostrophic.
Geostrophic.
Yeah.
Right? So I'm saying that the wind in this scenario is not geostrophic, the actual wind. We won't have to assume that it's geostrophic. But there's a component that is geostrophic. But do you understand this is the, look at, are you guys? I'm waiting for Nick.
Mm-hmm.
Oh, are you looking at me, Nick?
Yeah, I am.
Oh, okay. I thought you were writing something down. This is the advection of the pressure gradient. The pressure gradient force points which way?
From high to low.
Okay. This is a vector, del cross P. The geostrophic wind is a vector. Those two vectors are perpendicular. Is the geostrophic wind crossing the isobars? Does the geostrophic wind cross the isobars?
No.
No, it's parallel.
Then can it advect the pressure gradient?
No.
Right? So what I'm going to say is here is that this is going to be equal to this equation, tendency, plus now I'm going to go, it's the geostrophic wind plus the ageostrophic wind times the pressure gradient plus W dP dz. Does that make sense?
Mm-hmm.
But, and this is something you should prove by looking at vectors. Vector A plus vector B times vector C is equal to A dot C plus B dot C. And you should probably do this by looking at IJK, whatever the numbers are, and prove this. Because this becomes, add the two vectors, then take the dot product, and you still get a scalar. And these are two scalars. So this is true. So if that's the case, do you agree that I can rewrite this equation down here as
Okay.
okay? Now, I'm going to write something up here, off to the side. Do you remember that this times this, those are two vectors, is equal to the magnitude of one times the magnitude of the other times what? Remember the identity?
Cosine of.
Well, whatever the angle is,
Yeah.
right? So if you remember this, it's the cosine of the angle. Well, what is the angle between the pressure gradient and the geostrophic wind?
90.
What's the cosine of 90?
1.
0.
0. Okay.
Right? Sine of 90 is 1. The cosine of 0 is 0. So in other words, this term goes to 0. Does that make sense? Because I just said the geostrophic wind is not advecting the pressure gradient force. What's the only thing that can advect the pressure gradient force? The ageostrophic wind.
The ageostrophic.
Right. And the magnitude of this times the magnitude of the pressure gradient times the cosine. And what's the cosine? What's the angle between those two vectors?
They're parallels.
So it's just
0.
it's just the two magnitudes multiplied together. That's how strong the advection is. So what I have here, this yellow circle actually becomes this yellow circle. And what that means is I have the ageostrophic advection of the pressure gradient. I have here, this is what? That's the local pressure tendency, the local rate of change. And then what's this? What would you call this?
Change in pressure with height.
But it's multiplied by what?
Oh,
Vertical pressure advection.
Right.
vertical advection at the PGF.
What that will then allow me to say is that this term is around 10 millibars per day. This term, the ageostrophic, and I think maybe in the book they go ageostrophic, but they say that this vector is actually what they call this vector. So I want you to keep this in mind. That sometimes you see the perturbation. This little guy, the little prime, means the one that falls outside of. So ageostrophic and that symbol are the same. Just keep that in mind, okay, guys? This is about 1 millibar per day. And this is about 100 millibars per day. And the reason is, oh, I wish I had a little bit bigger of a board, but let's do it this way. W dp dz is actually minus W times rho times G. Which means, to a first approximation,
The first W is the lowercase one, right?
All the W's are there's no capital W.
Okay.
W as opposed to omega.
Man, I cannot. I have such a hard time telling those apart.
Well, then you need to make sure that your W's are pointy and your megas are rounded.
I always put a loop through my omega. Kind of have a little loop there. That's how I usually tell.
I think I might try doing that then. Putting a nice loop on it. Alright. I think I got it.
What do you mean a loop?
Oh, I like to actually I know with my omegas, I've been actually just straight up connecting the lines on each side.
I don't know if you can see my tablet here, but
I can't see it. No, you're
it's the. No, it's still not working here. Let me get the background out of here. And it's can't see because of the light coming in. But basically, I just put a loop in the middle. Kind of.
Do it again. Now I can see you. Because you're shrunk on that screen. I don't have enough students to make it larger.
There was light coming in through the window, so you couldn't see it anyway.
Well, in any case, make sure you know the difference. Yeah.
Yep.
Gotcha.
But what I'm saying is that omega is about minus rho g, right? Rho is going to be 1.25, g is going to be 10 times w. So we usually measure omega is in microbars per second, as opposed to millibars. And that's going to be about centimeters per second. So those are approximately equal to each other. I'm going to let you into a little something of something we discussed yesterday.
In Tuesday.
No, I discussed it with.
Oh, sorry.
Or the discussion was being had. I shouldn't say I discussed it with anybody. So.
Here comes the omega. There it is. That's as best as I can do it. It's going
Got
in
it.
and out, but it works. But yeah, loop.
Oh, a loop in the bottom of it.
Yeah, think of like the
Yeah.
Washington Nationals logo, something like that.
Yeah. There you go. That makes sense. So here, if you take a look, they've introduced a new variable in the models, dz/dt.
That's a question.
Right? That's the vertical velocity over time. That's vertical velocity change. Because they've added 700 millibar dz/dt to that in the RAF. We are using 700 millibar vertical velocity, but I'm wondering the differences between the two. In some cases, I might prefer dz/dt as a variable that's easier to get. Found the text. It says a second vertical velocity field will be included in the output files and written by the model as dz/dt in meters per second. It treats it as a prognostic variable. The vertical velocity, pascals per second, found in the current operational is now derived from dz/dt using the hydrostatic approximation. Well, isn't that what we've just done?
Mm-hmm.
W is dz/dt. That's what we said. And we used the hydrostatic to get to omega. So one of them is dz. The second are the units, meters per second versus pascals per second. If dz/dt is the parent variable, and I feel that's a reason to use it over vertical velocities, right? And 1 pascal is equal to 1 pascal per second is 0.2 meters per second. That's not exactly right, but it's close. Then Victor, but dz dt is the explicit solver in this case. Unless the vertical velocity is explicitly solving for w, it will almost always be sigma coordinates that are interpolated to pressure levels, then analyzed as a function of time. In other words, dp dt. But what's dp dt? dp dt is what? That's omega.
Omega.
Oof.
Which unit scale from pascals per second following the omega equation. FV3's vertical coordinate system, 2 9 hydrostatic solvers for vertical velocity, and the pressure perturbation are being integrated into NCEP's UPP code. And so when we look at what it looks like, here's your upward vertical velocity in microbars. That's what this says right here, microbars per second. And they're using all these huge numbers. But now we put it into meters per second, and it looks the same. It's a better, higher resolution. Right? And these are all meters per second. So if we're talking about a meter per second vertical velocity, where must we be?
You're in the updraft.
All right, we're in a thunderstorm. We ain't getting synoptic scale motions of meters per second. We are in the updraft. So by showing you this plot, and we are actually plotting out also helicity values, we're showing me where the 500 millibar or the 700 millibar vertical velocities are very high. But if you recall, and we've done this, we did this back, so you should go back and refresh your brain. We go to this guy. I can redraw it. Remember this little chart where we talk about convergence and divergence? And we say that the vertical velocity is going to be, where does the vertical velocity get maximized? In this case, upward vertical velocity. Where? Do you remember where we said the strongest vertical motion is?
Is it the LCL?
No.
Oh.
What is that?
L&D.
So is 700 millibars going to be the maximum speed? No, probably not. But if we assume 700 millibars is very strong, we are probably going to get some pretty good rising air up to that point. So wherever by 700 millibars we see strong vertical velocities, that tells me the air must be doing what from the ground to that point, which is only maybe 3 kilometers up.
Convecting?
Well, it is convecting, but what else must the vertical motion be doing?
Accelerating.
It must be accelerating, right? Rapid acceleration. So what we do is we use these products, especially this product, at a convective allowing model to show me where do I think the low-level updrafts are strongest. The low-level updrafts will be super strong when I'm stretching vorticity. So if I want to find helicity swaths, which I do, I'm going to look for strong upward vertical velocities at 700 millibars because that's low-level stretching vorticity. So when I go over here to a model, for instance, and I go to the HER, we've been using that. Well,
Excuse me.
it probably is not going to help unless I use some more way to this out. Right? I'm finding that to find updrafts. The strongest updrafts are right there. There's one over southern Louisiana, just a little bit. And unfortunately, we tried to overlay this with vorticity, surface vorticity. We thought, oh, that would be so cool. Put updraft velocity, low-level updraft velocity over surface vorticity, and then we can find land spouts. The problem is, what is vorticity? Vorticity is a change in the velocity over a distance of some sort, right? There's some velocity change over a horizontal distance. The thing is, these models have such a small grid spacing that any change is going to show up as a lot of vorticity. So all the grid points are too close, and we see vorticity, and it's too messy. So we can't do that. But what we have done, I believe, is we can use the wrap and look at vorticity. On the wrap, and we see areas in southern Louisiana, right on the coastline, where we have a lot of surface vorticity, and the fields are somewhat reasonable. And we've overlaid it with Cape. But what would be nice is if we could overlay it with 700 millibar vertical velocities. But the vertical velocity fields are so widespread, they don't allow for convection. So do you see the problem? Vertical accelerations, the DZDT terms, or whatever you want to say, omega, are only making sense on the convective scale. But the vorticity fields get too messy on these high scale models. So I have to use it on a model like the RAP, which is a broader region. I see better patterns. It's just like trying to do 500 millibar vorticity on a convective scale model. I'm going to get messiness really fast. So as a result, I can't put them on the same model. There's a limit to the usefulness of a model. But it does make me wonder, well, I don't have severe thunderstorms forecast. Well, a stronger storm or two could conceivably occur near coastal Louisiana or near coastal parts of Mississippi, Alabama. Latest thinking continues that inland destabilization will be. So in other words, we see it way far south. They're not going to put a slight risk there, but there's a possibility of severe storm right down in southern Louisiana. What do you guys think?
That's pretty cool.
Yeah.
But do you see how these things play a role? And when you start looking at microbars per second, you need to say, okay, what do you mean by that? It's a pressure change. It's an isobaric coordinate, right? As opposed to height as a vertical coordinate. So we talk about isobaric as opposed to something else. But all of these terms, vorticity, divergence, and geostrophic wind is non-divergent, right? If you look back at what we did, it's non-divergent because they're perpendicular vectors. So it's only the deviation from the geostrophic, the ageostrophic deviation, that results in pressure changes. That's what's causing the atmosphere to change. We say that the atmosphere always wants to go to geostrophic, it always wants to go to hydrostatic. If the atmosphere were always geostrophic and always hydrostatic, there would be no fun weather at all whatsoever. Because all the good stuff is the deviation from it. It's you disturb a situation, and that's what causes things. So I have geostrophic wind. Imagine geostrophic flow, and the atmosphere is absorbed to that. That's great. But now I go over a mountain, and I deviate the wind because the mountain's forcing the air to change. That ageostrophic wind is now going to advect pressure fields. And when I advect the pressure field, I get tendencies and pressures change, and that changes the wind everywhere. So one little disturbance anywhere in the atmosphere can be amplified. And if that small disturbance is amplified, then I get these big storm systems. And that amplification comes about through baroclinicity or baroclinity, where small disturbances amplify. And we will be talking about that in terms of the thermal wind. So you should finish this chapter in terms of reading. You've got your assignments. Is there anything else that's kind of super important? Yeah, we've got some important things. I would just finish reading. Try to understand this chapter a little bit more. We'll finish this up. If I go to the next chapter, weather systems, I mean, this is more synoptics, and we're not going to teach synoptics. And deep convection, it's amazing. We've already done so much of this in terms of mesoscale, but it's a nice reference there. And then they talk about boundary layers and climate variability, which we're not going to get into for this class. So we're finishing up this section. We have thermodynamic energy equation. We've got baroclinic, barotropic, thermal wind. That's where we're headed to. And we have next week to do it. So I think we're going to be fine. But you should be finishing up on your project. And I think we've covered 90 to 95% of everything that's necessary. Is there anything on there that we're still going to be talking about?
Got the thermal wind on there.
Thermal wind. So that's what we got to do. I think that's it. Maybe the energy cascade.
Yeah.
Yeah.
Okay, so those two things. So one of them we'll finish up on Tuesday. Fair enough, guys?
Fair enough.
Mm-hmm.
All right.
Yeah.
Well,
Just to make sure I have it written down right, 7/18, 7/19, 21, and 24.
yes.
Mm-hmm.
All right.
So 18, 19, 21, 24. All right, guys, do that and send an email to me, okay?
All righty.
All right, have a nice weekend. We'll see you later.
You too. Bye-bye.
Again, Paul. Take care.